making of a heart rate monitor made using the Cyclone for FPGA and the Nucleo-F429ZI MCU. And of course a custom PCB for filtering. So the PCB consisted of a difference amplifier and a non-inverting amplifier stage. If you basically use the relevant equations for those two, you can actually determine the gain. And for the cutoff frequency, which is relevant because we want to eliminate the higher frequencies above the mains and beyond, like any noise and everything, I plotted a cutoff frequency versus feedback capacitance graph here using a Desmos graphing calculator, and for around 1 nanofarads basically it's very high, so this is for the difference amplifier stage, so it basically doesn't play a part in it. But for the non-inverting amplifier stage I do the same thing, and I picked a value of around 100 nanofarads, which is around 10 to the power minus 7 here, so that's around 15 to 20 hertz, which is a bit below mains cutoff frequency, and that seemed to work. So here's a simulation, and here we have a nice band pass of the range we like, because you know heart rate is around 60 to 200, which is around this range, beats per minute, so that's around this range. And here is a prototype which seemed to be working alright, and then of course the PCB was built and it seemed to be working fine as well. And of course other tests were done, but here I've only put the board plot. And then comes the FPGA part. So the story begins with this little guy, ADC SPI. So it communicates with the onboard ADC, which is an 8-channel 12-bit ADC, using 16-bit SPI, and it gets a 12-bit ADC data from that. And also, whenever it's done with an SPI cycle, it asserts a SAM save signal here to signal it. So here it uses 16 states. So this is a very lazy method of doing this. Actually, later I'll show you the other SPI module I've made for communicating with the MCU. I use shift registers, but here I've used 16 states, and after the 16th bit is 16 bits are actually interchanged, I have a save state where I've asserted a SAM save signal here. And as you can see, this guy runs on a 1M clock. This is actually because of specifications of the ADC, but the rest of the system runs on 50M clocks. So I need to use, so this SAM save pulse is actually a 1M clock pulse, which lasts for 50M clock cycles, and that wouldn't work. So we would actually be saving 50 copies if we just connected that to the SC-FIFO. So I'm using some little guy in between called an RH detector. So I basically detect a rising edge and just causes one pulse for each pulse. Each 1M pulse just results in one 50M pulse, and therefore it's only saved once. Good. So that makes it that basically takes place every 5 milliseconds. So our sampling rate remains constant at 200 Hertz, and it's all saved into the SC-FIFO by asserting the right request. So now let's go to how is this data retrieved from the SC-FIFO. So this is where the MCU comes in. Well, because the MCU is basically what wants the data, right? So the FPGA communicates with the MCU using 16-bit SPI again, but here I've used a shift register, and whenever it's in the SPI cycle, a busy signal is asserted. So the busy signal is basically the busy signal is basically an inverted negative chip select signal, but just for the sake of just for the ease of understanding my code, there's a busy signal here. So whenever busy is low, whenever busy falls, it means we're done with an SPI cycle, right? And whenever busy rises, it means we're starting an SPI cycle. This is important because whenever it falls, we need to save the sent data, and whenever it rises, we need to load the data to send. So this is also important. So here, this guy, you should also keep in mind, is synchronized to the MCU clock, not the 50M clock or the 1M clock. So we need to synchronize this guy with these clocks. So the 1M clock I didn't have to synchronize because the 1M clock is basically the 50M clock just divided. So it's basically synchronized to the system, but it's just lasts longer. I mean, it's different frequency, but it's synchronized. But here, this guy is not synchronized, so it could cause like various hazards. So, so because of this synchronized is used, which is basically 3D flip-flops connected in series, all synchronized to the 50M clock that's used here. So whenever we detect a falling edge, or whenever you detect a falling edge in this, so whenever you detect a falling edge in the busy signal, the data that's loaded to that is from the MCU SPI module is saved into the register here. And this is then used all over the system for various purposes. So now let's go to retrieving data from the SCFIFO. So the 10th bit sent by the MCU is a control bit that says, okay, I'm expecting ADC data in the next cycle. So whenever the 10th bit is asserted, I look for a rising of the MCU SPI busy. As I said before, rising means we're starting another SPI cycle. So if the latched 10th bit, which means the previous 10th bit, is high, and now we're starting the next cycle, then we want data from the SCFIFO. So this rising edge causes a pulse in the ADC read request signal here that causes the SCFIFO to load the bus here that's sent to the MCU SPI module with the data, with the top data, with the data, with the relevant data. So yeah, that's how it basically gets the data. So to sum up, the ADC SPI saves data into the SCFIFO every 5,000 1M clock cycles, and the MCU SPI, if it wants data in the next clock cycle, asserts the 10th bit, and this causes during the rising edge of the busy signal for the next SPI cycle, it causes the SCFIFO to load the transmitting bus, the TXMCU bus, with the relevant data. Hope that is clear. Now let's move on to the LCD. So now what's up with the rest of the data sent by the MCU? So the 10th bit, of course, is saying that I'm expecting data, ADC data, in the next cycle, and the 11th bit, because it's 0 indexed. The 12th bit says that the first 10 bits I'm sending are actually LCD bits. So if the 11th bit is deasserted, it means no, disregard the first 10 bits. But if it's asserted, save this somewhere. This is for the LCD. So again, I'm looking for a falling edge of the busy signal, and it's synchronized with the synchronized busy signal, of course, otherwise this could cause hazards. I'm looking for a falling edge in the synchronized busy signal, and with a little bit of a delay here. I'm having a couple clock cycles delay because it takes one clock cycle here to save keep doing that, to save the latch data sent by the MCU. So I'm having a delay here, and to make sure that this is indeed data from the current cycle, because so to make sure that this is indeed data, the 12th bit of the current cycle data, and then if so, this asserted this pulse is sent through into the write request signal for this SC-FIFO buffer, which is a different guy. So to sum up, if the 11th bit of the current data bus, if the 12th bit, of the current data bus is asserted, the first 10 bits are saved into the SC-FIFO buffer. So again, just like this little guy continued to save data into the SC-FIFO buffer, just trusting that somebody was reading it, otherwise the buffer would just overflow every 5 milliseconds. Here, the same thing happens, but the MCU is just writing to the SC-FIFO buffer, trusting that somebody is sending this stuff to the LCD, otherwise the buffer would overflow. And indeed, there is a little guy here, the LCD write, to write this data into the LCD. So let's go into this guy. So the first couple of states are for initializing as per the documentation of this specific LCD I'm using, and then it comes into the idle state. And okay, I need to show you something. So here it takes in a signal, the buff empty signal, and whenever the buffer is not empty, so whenever the buffer is not empty, here you can see whenever buff empty is 1, it goes back to idle. So whenever buffer is empty, it goes back to idle, but whenever buffer is 0 or not empty, it goes into buff read. Buff read is basically asserting a read request signal. So you can see buff read here is asserting a read request signal, and then it goes into write E high. So enable is high, then enable low for the clock, for the LCD display. So it's basically clocking this data into the LCD. This is as per the documentation, and these need to last basically 1 millisecond, again as per the time requirements of the LCD. Therefore, this module is actually running on a 1M clock cycle. So here it says 50M, but it's actually running on a 1M clock cycle. That's a mistake there. So this is running on a 1M clock cycle, and so I need to basically keep that in mind. Can't just send it into the buffer, otherwise, I can't just send the read request signal into the buffer, otherwise I'll be reading like 50 samples, but only just looking at one, so I'll be basically wasting samples, and that wouldn't work. So I need to keep that in mind. I need to detect a rising edge again. So yeah, that's how this works. Again, here, as I've said right now, the read request signal is sent through a rising edge detector to transfer this 1M clock pulse into a 150M clock pulse, and this causes the buffer to load this data bus with whatever the data it has. So to sum up, it looks if the buffer is empty. If it's not empty, asserts a read request signal, transfers which this module transfers into 1 pulse, 150M pulse, and this causes the buffer to load with data. This continues until the buffer is empty, and whenever the buffer is empty, this guy waits in the idle state. So as you notice, this looks if the buffer is empty, but how does the MCU know if this buffer is empty, right? Well, good question. I'm glad you asked. So as you can see, the first 12 bits are, of course, the ADC data, and the other 4 bits of the 16-bit SPI are 0 because they're connected to ground. But I'm using 2 other GPIO IO pins from the Cyclone flow. So the Cyclone flow FPGA is in Altera DE0 nano board, and there are a couple GPIO pins, and I'm using 2 of them, and 2 GPIO pins of the DE0 nano board to actually connect the almost empty and almost full bits. So the almost empty and almost full values, as specified by the parameters of the SC-FIFO, are 90 and 10. So whenever there's 10 more samples remaining, so whenever it reaches whenever it's not almost empty, which means there's more than 10 samples, the MCU keeps getting a load of data, gets a batch of data, does calculations on it. Well, basically adds it to the set of data it had gotten before, and like does its calculation, which I'll show you, until it's almost empty. And then, so the buffer basically carries on getting data from the ADC while this is going on. But all in all, because I'm not using the empty and I'm only using almost empty, the buffer never really gets empty, and therefore, there's no risk of losing data like that. So yes, there is no risk of losing data like that. The buffer never gets full, because whenever it's almost full, I'm of course starting to get data, and then until it's almost empty, and so the buffer never loses data. And that is that. To sum up everything I've said here: 1. ADC SPI module saves ADC data into the SC FIFA buffer every 5 milliseconds. MCU knows if it's almost full. If it's almost full, gets a batch of data until it's almost empty, by communicating with the FPGA using SPI, which gets data until it's almost empty, and that happens on a batch of data. And whilst this is happening, this guy is continuously saving data into the SC FIFA. And simultaneously, if the MCU wants to actually say something, send LCD commands, it can actually do that by asserting the 12th bit and sending data, which is saved into the SC FIFA buffer whenever it writes. And then this guy, separate from all of this other busyness happening in its world, is just only checking if the buffer is empty. If it's not, it writes to the LCD. Simple as that. I don't want to bore you explaining C++, so here's a pseudocode version of my algorithm for calculating the heart rate and sending display data.